Okay, I'm back at it. Okay, so all right. So wait, which scene? Okay. So I'm gonna try to be on the board for as much of this as possible. Okay. All right. So the first problem is find one solution. Find a solution for x dot equals x sine y and y dot equals y cos x. So we just take so this is a solution. So if we have, because you just pick the 0, 0. So that's an equilibrium solution. The This says exercises 1 through 14 focus on the basic ideas, definitions, and vocabulary of this chapter. Their answers are short, and you should be able to do them with little or no computation. They vary in difficulty, though. Okay, so this is 1. 2, find all equilibrium points of x dot equal to y and y dot equal to sine x times y. Okay, so we have so the thing is find the fixed points. So we have if y is equal to 0, the system is fixed. Okay, but similarly, if I think it's just that. I think it's literally just that. Oh wait, I actually did the wrong problem. This one's 5. This is number 5. Okay, fine. So let's do 2. So 2 is x dot equals y dot equals e to the y plus x squared. Okay, so we have 0, 0 is not fixed. But if y is 0, y has to be 0. Y has to be 0 because otherwise x dot is non-zero. So then we get 1 plus x squared is equal to 0. So, wait, no. Doesn't x equal I? Because then that becomes minus 1. I think that's the only solution, is that you have 0, 0, I. You're back. Nice. Okay, I'll be back in a minute as well. Okay. All right. So that's problems 1, 2, and 5. Okay, problem 3. Problem 3 is convert to first order. And the system is y double dot is equal to 1. So we're going to get y dot equals x, x dot equals 1. Okay, then problem 4 is general solution. So if dx dt is equal to 1, then we get x is equal to t plus c. And then so then dy dt is equal to t plus c. So then you get y is equal to t squared over 2 plus ct plus c2. Okay, that's the general solution. All right, problem 5, we did. Problem 6. Okay. Let's erase. Wait, actually, here's what my method will be. We'll double check our answers because really we'll never be able to tell if we don't double check our answers. So we did 1 through 5. All right. Yep, they got the. Oh, actually, yeah, I didn't even think of that, but that's fine. There's no real equilibrium points. One half t squared plus c1t plus c2. That was easy. And then this one is every point on the x-axis. Yep, great. All right, cool. So the first 5 were correct. All right. How many fixed points? 4. So this is 6. And the system is x dot equals x times x minus y dot equals x squared minus 4, y squared minus 9. Okay, so we have if x is 0, then y squared minus 9 is equal to 0, which means y is equal to plus or minus 3. So we have 2 solutions right here. Now if x minus y is equal to 0, then x is equal to y. And in the case that x is equal to y, we could write y squared minus 4 so in this case, let's see, this problem, I think, so then we get like 2, 2, minus 2, minus 2, 3, 3, and minus 3, minus 3. And then we get also 0, 3, and 0, minus 3. They said don't do a lot of computation, but I don't know how to solve that otherwise. So I got 6, but I'm gonna do this. So we have 0 is equal to x times x minus y, and we have 0 is equal to x squared minus 4 times y squared minus 9, and then we solve. Wait, can I assign? Oh yeah, I always forget this. Then you do solve equals xy. So we have 1. Is there like a count function? Okay, nice. So you get minus 3, minus 3, minus 2, minus 2, 2, 2, 3, 3, 0, minus 3, and 0, 3. Okay, so we got them all. So there's 6, but I don't know how they expect you to just like figure that out. How do you know? Anyways, so we had to just do that. All right, problem 7. Wait, I want to check something. All right. Seven is so this is e to the minus 6t to e to the minus 3t oh wait, this is 2x minus 2y squared, and then y dot is equal to minus 3. All right, so clearly this one, since it's decoupled, you're going to get y of t is equal to e to the minus, or c e to the minus 3t. And then, well, we could solve it, but we could just check. So why don't we just do that? So this is going to be, y dot is going to be minus 6 e to the minus 3t equal to minus 6 e to the minus 3t. So that equation checks out. Then this one is going to be minus 6 e to the minus 6t is equal to 2x Yeah. So 2x is going to be 2e to the minus 6t minus minus 2 times y, which is this squared. So 2y squared is going to be minus 4y, or 4y squared, which is wait. This is going to be 2 times 2e to the minus 3t squared, which is equal to 4 e to the minus 6t times 2. So this is going to be 8. So this is going to be 2 minus 8e to the minus 6t. So therefore, it is a solution. So yes. Yes is the answer. And so 8 is write a second order equation that and the corresponding first order system for the mass spring system with a spring constant alpha, mass beta, and damping coefficient gamma. Okay, so first off, I always like to just derive it, right? So you have F equals ma. M is equal to beta. Okay, and acceleration but we have that the force due to the spring is going to be equal to minus k times x, which is its position. And in this case, k is the spring constant for alpha. This becomes alpha. So we get x double dot is equal to minus alpha. But this is the force. This is ma. So this is going to be beta x double dot is equal to minus a x. But then it's also going to be minus what is it, gamma? Yeah, damping coefficient gamma x dot. So this is the answer. All right. Nine. Find the general solution for x dot equals 2x, y dot equals minus 3y. I mean, this one you should be able to do without even thinking, right? It's just going to be x of t is equal to ce to the 2t, and y of t is equal to ce to the minus 3t. Want to see that? All right. I wish this thing was slightly higher. Maybe I'll move it up at some point. It'd be really nice to have this thing, because then the highest point, you can write the problem up here and then actually do the work at a good height. Okay, 10. Sketch the graphs. Sketch. For IVP x dot equals y squared minus 4y dot equals all right, so we need to solve this. Oh wait, no. You know why we don't have to solve this? So these are the tricks. You need to recognize when you need to be fast. If we find the fixed points, so if y is equal to plus or minus 2 and x is equal to 0. So this is already at a fixed point. So so it's just going to look like, so x of t is going to look like this. So x of t is equal to 0 and y of t is equal to 2. So this is t, x of t, and then t, y of t, and this is going to be like that. So that's it. All right. Okay, 11. Give an example of a first order system of differential equations with exactly 10 equilibrium points. The product of x minus I from 1 to 10. So you'd get, x minus 1, x minus 2, x minus 3, x minus 10. That one's fun. 12. Suppose f of 2, 1 is equal to 3, 2. What is the result of one step of Euler's method? I'm not doing that. I don't give a crap about Euler's method now. Actually, let's do Euler's method. Let's do Euler's method. Okay, so we have f of 2, 1 is equal to 3, 2. We have the y dot is equal to f of y, and then we have y of 0 is equal to 2, 1. Now we want delta t is equal to 0.5, and we want to just do one step. Okay, so if we just take the x component, so we have like let's say we're at some curve, and right here, this is 1, but this is 2, and then we want 2.5. So we're going to have 2 plus okay, and then the next step is going to be 1 plus So these. So let's double check, but I think it's 3.5 and 2. 3.5 and 2. Okay. Nice. All right. 13. Sketch the solution curve. Oh, it just goes right to the center. We don't even need to do that one. Suppose that all solutions of the system tend to an equilibrium point at the origin. What can you say about the solutions to? Oh, they go away. They diverge. Okay. Oh, true false. I love true false. Wait, didn't we just do this problem? Wasn't it number? Oh wait, no, we didn't. So you get -6. No, I think we did do this problem. And it's true. Oh, these are the review. Oh, this is the review. 15. True, yeah. X equal to 2. The function x of t equal to 2 for all t is an equilibrium solution of the system. That's false. 17. Two different first order autonomous systems can have the same vector field. Two different first order autonomous systems can have the same vector field. Ooh. That's a really good question. I don't know. "17" is false. And it's because suppose we have one solution from each of them, then they must be the same solution because they share a point. Let's see, how do they answer it? Yeah, okay. That makes sense. Yeah. All right, that's fine. Two different first order autonomous systems can have the same direction field. That's true. If you like scale one of them. "19" is true. What? How is that? I don't understand that at all. Okay, but the same point. So you can't assign a single valued. What does that mean? So okay, so autonomous, yeah, means it doesn't depend on t. Well, you can't. X of t is equal to sine t. Y of t is equal to sine t. So this. Why that fails autonomy? Notice that sine t revisits the same point. Okay, I'm starting to see it. Yeah, that makes sense. That's kind of weird though. This one is true. 19. Wait, hold on. No, 19 is. Or, I mean, sorry, 20 is true. Yeah. if the function cosine is a solution to a first order autonomous system, then the function that's true because they intersect at some point and their partial derivatives are good. So 21 true. 22. Okay, so we're done with true falses. All right. Macquarie Island is a small island, bro. Nah, too wordy. True false. Solution curves give several solution curves for several solutions for the system are shown. The solution curve corresponding to the initial condition 1, 0 includes the point 0, 0. That's false. The x of t and y of t graphs of the solution the initial condition 1/2, 0. Wait, what? It's hard to tell. Wait, 1/2, 0? That's false. I think that's just false. 0, 1. The solution with initial condition 0, 1 is the same as the solution with initial condition 0 minus 1. No. So it's true, false, false. The function y of t for the solution minus 1, 2. It's hard to tell, right? Like, because oh, okay. So wait, so 1, 0. Wait, 1, 0 is not a fixed point. 0, 0 is a fixed point. I'm pretty sure that this is true. 26 is true. Okay, the function y of t for the solution. The functions x of t and y of t for the solution with initial condition -1. Shoot, I would have said true. Why is it that it? Wait, dy. So okay, we're at this point -1, 0. So dx is gonna be 0, but dy is gonna be -2 -3. What? It is. It is decreasing. Yeah, I don't understand why they're saying this is false. Just move on. The phase portrait of a completely decoupled system. In the straight lines are along the axes, I think, is really what it is. Solutions move along a straight line on the x and y axis. Let's see if that's the right answer. I didn't want to do that last one. That last one, it's like the equilibrium points are like 1/2 pi, 1/2 times pi over 2 plus k pi, and then you just set, you know, a pi over 2 plus k pi equal to x, something like that. Let's just look at the answer just to make sure that 29. Yeah. Wait, cos. Wait. Oh, that because that's x. Yeah, that's x, right? And it's just gonna be okay. So that's what I thought. I said it moves along straight lines on the x and y axis. Null lines are straight lines. Yep. That's an interesting way to put it. The phase portrait is just a Cartesian product of the one-dimensional phase lines. That's fun. I like that way of saying it. It's gonna be an offset sign. So 32 might be good. 32 is like starts at y starts at 1 and then it just sort of goes down to 0. X on the other hand goes negative and comes back up. So it goes like whoop. Okay. And this one is going to be just like a sine cosine thing. So x is going to start by going from 1 down, and y is going to be start going from 0 down. Okay. This one, let's see, y starts at 2, and it goes down and it levels out. And then x starts at 1, x starts at 1, and then goes down to like a half. And then it goes up to 2. All right, this one will do. I like these ones because they're just like practice. Okay, so we have so A, general solution. B, fixed points. C, IVP for -1, 3 as the IC. And then D is like use a system solver or something like that. Right. So okay, so we got that. So then x dot becomes, let's do this, x dot minus x is equal to 2k2 e to the 3t plus 1. Okay, then the solution here is so in this case we probably want to use we want to guess, but if we guess x, so first off we want to solve the homogeneous system. So the homogeneous system is going to be just equal to k1 e to the t, because it's just this part of it. But our particular solution we can guess as a e to the 3t. But the problem here is that we're going to get 3a e to the 3t minus a e to the 3t is equal to 2k 2 e to the 3t plus 1, though. I mean, this plus 1 is going to be a problem. So I think what we want to do is we want to do plus t, because then we're going to get a, because then this becomes plus 1. No, but then the t, what if it's like, if it was like plus bt, then we'd have 3a e to the 3t plus b plus minus a e to the 3t plus beta t, or bt. So then we get, 3a minus a is equal to 2k2, but then we'd also get shit. I'll be right back. I'm not sure. Okay, so this isn't going to work because you get b times 1 plus t is equal to 1. But there's just no way to make that work. If, however, we did integrating factors with u dot is equal to u times g of t, which is going to be minus 1, then we get this is going to be this is just going to be e to the minus t. So then we factor that through, but this isn't going to work. This is going to be brutal. Damn, this 1, bro. This 1 is causing me so many issues. So you have I think don't you just let your guess be plus 1? Couldn't we just do that? Yeah, what am I doing, man? Alright, so oh wait, I do need to have y of t is equal to k2 e to the 3t. Alright, but here, alright, now we've got it. This is, I don't know what I was doing. So xp dot is equal to 3a e to the 3t, and that's it. So then we get, so we can just erase this. So then this is going to be minus a e to the 3t plus 1. Oh, wait. Because this is like that. All right, so we get 3a minus a is equal to 2k2. So 2a equals, so a equals k2, right? So then x of t is k1 e to the t plus k2 e to the 3t minus 1. I think so. Let's double check. I mean, wait, we can double check actually on the board, right? So if we okay, so y prime, we're gonna get 3k2 e to the 3t is equal to 3k2. Okay, so that one checks out. That one's easy. Then we get x dot equal to k1 e to the t plus 3k2 e to the 3t is equal to x plus 2y plus 1. So it's going to be equal to 2x equal to 2k1 e to the t plus 2k2 e to the 3t minus 2 plus 2y. 2y is going to be equal to 6. No. It's going to be equal to 2k2 e to the 3t plus 1. So this becomes minus 1. Fuck it, I'm just gonna check the answer, man. Oh, we got it right. All right, that was correct. Nice. Okay. All right. Now we just have to find the fixed points. All right, so the fixed points. The fixed points are easy. Okay, the fixed points. Y is equal to 0, obviously. So then x equal -1. All right, that one was easy. What's next? IVP. Okay, so now we need to plug in. So y of 0 is equal to 3 is equal to k2 e to the 3t. But this is 0, so this goes to 1. So then k2 equals 3. And -1, x of 0 equals -1 is equal to, oh, this is going to be k1 e to the t plus 3e to the 3t. But this goes to 1. This goes to 1 minus 1. So then we get k plus 2 is equal to -1. Or k1 equals -3. All right. Damn. All right. These are getting boring, dude. I want to do something more fun. Let's see. What else is in here? Is there anything interesting in this thing? This is maybe interesting. So to solve this one, where's my notebook? I just want to do it sitting down, man. All right, so we have y dot minus y is equal to 1. So we're going to solve the second one first. And we're going to do it by integrating factors. So we let u dot equal u times -1, or minus u. And then we get u of t is equal to e to the minus t. So then we multiply everything by e to the minus t, and we get d dt of e to the minus t times y is equal to e to the minus t. So then we integrate both sides with respect to t. The integral of 1 over e to the t I think that's just going to be -1 over e to the t. So we get minus e to the minus t is equal to, and that derivative, that integral cancels out. And so we get e to the minus ty. So then I think you just get y equals -1. Wait, that can't be right. Wait, E. Yeah. Wait, we need to go back to. Oh, that's. I always forget that. This is a plus C, so then you get minus 1 plus C e to the C e to the T. Okay, yeah. All right, so then once you've done that, you can plug that in and you get you get x dot is equal to x times C e to the T minus 1 is equal to x C e to the T minus x. Oh wait, no, you don't want to do that. You want to keep it, so this is going to be linear homogeneous. So we should just be able to, and it's separable, right? So we're going to get dx over x is equal to C e to the T minus 1 dt. So then we're going to get, the integrate both sides, you get ln of x is equal to C e to the T minus T plus C. So then you get x of T is equal to x of C e to the T minus T plus C. So then you get e to the C T. All right, cool. So that's what I got. The equilibrium points, we got 0, 0. No, we don't have 0, 0. We have 0, -1. And we have -1 and anything. That's really what it is. Oh, no, no. It's just 0, -1. If we're at 1, 0, then we're just going to be along the y. So it just grows infinitely away along the y-axis. Oh. Oh. Oh wow. Okay, last one. Then we can be done. A simple model of a glider flying up and down the equilibrium points. All right. Theta dot equals s squared minus cos theta over s. And minus sine theta minus d s squared. Okay, so we know that we need s squared. So wait, oh. So if we write it as s squared equals cos theta, but we also need s squared equal to minus sine, or ds squared equal to minus sine theta. So s can't be 0 also. If s is like pi over 2, or no, square root of pi over 2, then you get, oh wait, no. If theta is pi over 2, if theta is equal to pi over 2, then cos theta is equal to 0. But if theta is pi over 2, then cos theta is equal to pi over 2. Then cos theta is equal to 0. But if theta is pi over 2, then cos theta is equal to 0. But if theta is pi over 2, then cos theta is equal to 0. But if theta is pi over 2, then cos theta is equal to 0. But that would mean that, okay, that S is... If theta is equal to 0, then cos theta equals 1. So then S squared equals 1. Okay, but if S is equal to 1, minus sine 0 is 0. Wait, how do you find the equilibrium point? Am I stupid, dude? What the hell? I feel like it's gonna be like... I feel like it's gonna be something like S is equal to like... I feel like S is gonna be equal to like... S is gonna be equal to like 1 minus sine theta, sine squared theta. So then you get... Or wait. S squared... No, S is equal to the square root of 1 minus sine squared theta. So then S squared... Oh, wait, no. All right, let's just look at this second equation. So S squared is equal to square root of cos squared minus 1. So then S is equal to the, what, the fourth root of that? It's got to be something like that. It's got to use the Pythagorean identity. There's no other way. I need some food, dude. I'm starving. Oh, what? That's crazy. That's a crazy one. Okay. That's it for the review, I guess. All right, the quiz is on 1.6 through 2.7. So maybe I'm going to do some more problems from these sections. Just to review. All right.